Number 4 on the 2019 exam. This is a related rates problem. Or it has related rates in it. Okay, so a cylindrical barrel with a diameter of 2 feet contains collected rainwater, as shown in the figure above. The water drains out through a valve, not shown, at the bottom of the barrel. The rate of change of the height of that water in the barrel with respect to time is modeled by dH dt is minus 1 over 10 square root of h, where h is measured in feet and t is measured in seconds. Volume V of a cylinder, this is basically volume for a cylinder, formula for it. Part A, find the rate of change of the volume of water in the barrel with respect to time when the height of the water is 4 feet. Indicate units of measure. So in this problem, you need the units. Okay, so how do we approach this one? What is this question asking for? It's asking for dV dt. Rate of change of the volume of water with respect to time. That's dV dt. Derivative of volume with respect to time. Okay, so we probably need to differentiate this guy with respect to time. Okay, let's be smart about it though, because if r is a function of t and h is a function of t, we need to use the product rule. Can we get away with not using the product rule if one of them's constant? Makes the product rule easier, per se. So technically we still need the product rule, but product rule, when we differentiate a constant, it's 0, right? So it makes the product rule much easier. And constants we can treat like, we can leave alone because we can, there's that property of derivatives. But anyway, so that's what I did over here. Basically, the radius doesn't change. It's a fixed cylinder, right? The radius doesn't change with respect to time. The height of the water does. It's draining, right? So h, you need to differentiate with respect to t, but r is a constant, so that makes it a lot easier. So pi r squared, treat it like a constant, so we just differentiate h with respect to t. So dv dt is pi r squared dh dt, okay? H is 4, they give us that. So, by the way, what's dh dt? That's right there. So I plug that in right there. H is 4. So dv dt evaluate at h is equal to 4 is, don't bother simplifying, just leave it like this. Units are feet cubed per second. Volume is feet cubed, time is seconds. So feet cubed per second. Okay. Part B, when the height of water is 3 feet, is the rate of change of the height of the water with respect to time increasing or decreasing? Explain your reasoning. Okay, so even this one, I read it incorrectly the first time, so you gotta be careful. What is it asking? Let's read it one more time. Is the rate of change of the height of the water with respect to time increasing or decreasing? So you might read this as, it's asking if the height of the water is increasing or decreasing. That's not what it's asking for. It's asking for, is the rate of change of the height of the water. So let's go back real quick. If it were asking, is the rate of change of the height of the water increasing or decreasing, that's dH dt. But it's asking for the rate of change of the height of the water. So you need to differentiate dH dt. So it's the second derivative of h with respect to t. That's what it's actually asking. So even when I read it quickly, I misinterpreted it. So you got to read it carefully, okay? So it's asking for second derivative, as I said. So we got to differentiate this with respect to time. That's right there. Don't forget implicit differentiation, okay? Or chain rule, technically. So it's asking for the second derivative at h is equal to 3. Okay? So, by the way, we had dH dt when h is equal to 3, right? Or actually, it's with respect to h already. It's a function of h. So, we already have that. So, that's what I replaced, again, dH dt with, right there. Yeah? Okay, so this, plug in h is equal to 3. We see that it's positive. We don't care about the actual value, so I just wrote greater than 0, because negative times negative is positive. So because the second derivative is positive, dH dt is increasing. Okay, so that's all you need to say. It's positive, so dH dt, or the rate of change of the height of the water with respect to time, is increasing. That's all you need to say. Okay? And then part C, at time t equals 0 seconds, the height of the water is 5 feet. Use separation of variables to find an expression for h in terms of t. So this is just solving the differential equation. So that's over here. Move all the terms with h on one side, move all the terms with t on the other side. Integrate both sides. Yeah, so over here is just power rule. Over here is also power rule. Okay, so here, you can start solving for h here. That's totally fine. But here, I plugged into initial condition. At t equals 0, the height is 5 feet. So h is 5 when t is 0. So I find that my c here is 2 root 5. So now I plug the c into there, right here. And then here, I start solving for h. And then you should get this as your h of t. H of t, I don't think that's important, but this is the answer right there. Okay, as I said, you could start solving for h there from here, and then plug in your initial condition to find your c. You might get a different c, or actually you should get square root of 5 as your c if you did it like that. But usually, I plug it in right from the beginning because sometimes, it depends on the problem, the math is easier to do it from here. And so over here, you have to like square root and stuff like that probably. But anyway, not too bad, but just from habit and experience, usually I just do it from up there. Unless I clearly see it's much easier to do it from down here. All right, that's it for this video. Hopefully it was helpful. The confusing part for this one was definitely part B, in my opinion. You got to interpret it carefully. Read it carefully, interpret it carefully. It's asking for a second derivative, not first derivative, okay? Please give this video a like if it was helpful, and hopefully I'll see you in another video as well. Bye.